Now in section 2.3, we'll be calculating limits using the limit laws. In the previous section, section 2.2, we used calculators and graphs to guess the values of the limits. But we saw that such methods don't always lead to the correct answer. In this section, we use the following properties of limits called the limit laws to calculate the limits. So what I'll do here is I'm going to use and state these laws verbally, which is what is here on the right hand side. But in order to have these laws, we have to say that c is a constant and that the limits as x approaches a of f of x and x approaches a of g of x exist. Now the first one is the sum law. And how we would say this is that the limit of a sum is the sum of the limits. We have the difference law. The limit of a difference is the difference of the limits. The constant multiple law. We would say that the limit of a constant times a function is equal to the constant times the limit of the function. The product law, we would say that the limit of a product is the product of the limits. And the last one, the limit of a quotient is the quotient of the limits provided that the denominator does not equal 0. Okay, let's first take a look at example number 1 using this following graph and evaluate the following limits. Now for part A, we have the limit as x approaches -2 of the sum of those functions, and the second function is being multiplied by the constant. So let's go ahead and use our limit laws first before we evaluate this. Okay, so we have the limit as x approaches -2, and we're expanding this using the sum law of f of x, plus the limit as x approaches -2, 5, which is the constant times g of x. Okay, now the limit on the right hand side means that now we need to use that constant rule so that we can write now this is 5 times the limit of that function. So now this becomes the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. Now we come up here at the graph. Let's take a look at where -2 is on the x-axis, and we can see that for the function f, that's the one that's in red. So as x is approaching 2 from the left, and -2, excuse me, from the left, and -2 from the right, we can see that the limit is going to be 1. Plus 5 is the constant. Now we got to find the limit of g of x as x approaches -2. So again, looking back at where -2 is located, now looking at the function g, so as x is approaching -2 from the left and -2 from the right, we can see that that limit is -1. So now we just need to evaluate using order of operations. So 1 plus 5 times -1 then becomes -4. Okay, let's take a look at the next example. The next example is the product law for the limits. So we would expand this by saying the limit as x approaches 1 of f of x times the limit as x approaches 1 g of x. Okay, now let's take a look at when x is equal to 1 and according to the function f. So as the limit approaches 1 from the left and from the right, we can see that the limit would then be 2 times. Now let's check and see what the limit is as x approaches 1 of g of x. So again, here is 1. Okay, now when you see that the limit as x approaches 1 on the function g of x, okay, we can see that that becomes -2. So we have the limit as x approaches 1 from the left of g of x is equal to negative 2. Okay, and then as the limit as x approaches 1 from the right of g of x. Okay, so as you're moving it from the right of this blue function, well, the limit of that is 1. And since they do not equal each other, well, then we can't even simplify this. So we would say that this limit does not exist because of this limit here on the right side. Okay, now let's take a look at C. Now this is the quotient law. Okay, so again, using the quotient law, we would say that the limit of the numerator as x approaches 2 of f of x, and then we're going to divide that by the limit as x approaches 2 of g of x. Okay, so let's take a look at when the value is 2 and then looking at the function of f, which is in red. Now, as the function is approaching 2 from the left and 2 from the right, we can see that it's probably like midway, maybe about 1.4 or 1.5. So we're just going to say it's approximately 1.5. Okay, now let's take a look at when it approaches 2 on the function of g of x, which is the blue. So as it's approaching 2 from the left and from the right, well, it's going to be 0. Well, what do we know about anything being divided by 0? We would say that this is undefined. Okay, now if we use the product law repeatedly with g of x is equal to f of x, we would then obtain the following law. So this is the power law. The power law is saying that the limit as x approaches a of f of x to the nth power is the same thing as taking the limit as x approaches a f of x to the power of n when n is a positive integer. Now, in applying these 6 limit laws, we need to use 2 special limits. Okay, now the limit as x approaches c equals c. Okay, now keep in mind that this is a constant. So when you have a constant, well, what it's doing is it's representing a constant function, which is a constant line here. Okay, and then the limit as x approaches a of x is equal to a. Well, this is a linear. So that means that if you had a here and another value a here, so you would have this limit as x approaches a, x is equal to a. Now, these limits are obvious from an intuitive point of view. Okay, state them in words or draw graphs of y equals c and y equals x. So y equals c again is the graph of this function here, and then y equals x is then the graph of this function. So you can see how the limits are associated with those two graphs. Now, if we put f of x is equal to x in law 6 and use law 8, then we get another useful special limit. Okay, and that means that the limit as x approaches a of x to the nth power is equal to a to the n. Okay, now another way of looking at this is that if we have the limit as x approaches a, okay, and that is x to the nth power, okay, and then using our rules, we would then say, okay, well, this is now the limit as x approaches a of x, and then this entire limit is then being raised to the power of n. Now, if x is approaching a, then the limit of that function x would then equal a to the nth power. And we'll elaborate more on that as we go along. Okay, now there are other limit laws here, so additional limit laws. So a similar limit holds for roots as follows. We can say that the limit as x approaches a of the nth root of x is equal to the nth root of a, where n is a positive integer. If n is even, then we have to assume that a is greater than 0. Okay, and then more generally, we have the following law. The limit as x approaches a of the nth root of f of x is equal to the nth root of the entire limit as x approaches a of f of x, where n is a positive integer, and if n is even, then again we assume that that limit as x approaches a of that function is greater than 0. Okay, now for example number 2, they want us to evaluate the function limits and then justify each step. Okay, so let's go ahead and do that. So for the very first example, we have the limit as x approaches 5 of the function 2x squared minus 3x plus 4. Okay, so by justifying, we're just going to use the laws that have been given from 1 through 11. And we're going to decide, okay, which law is doing what. Okay, so on the first one, okay, we can see that this becomes the limit as x approaches 5 of 2x squared. So this represents the first rule. Okay. Then we are going to subtract the limit as x approaches 5 of 3x. And again, justifying what rule is this, which is rule number 2. Okay, and then we have plus the limit as x approaches 5 of the value of 4, and therefore that represents step number 1. Okay, so now what we want to do is we want to rewrite this limit so the constant is on the outside. So we're just going step by step. It's kind of like order of operations. So now we're going to write 2 times the limit as x approaches 5 of x squared. Okay, so that rule is rule number 3. Okay, and then the next one we have minus 3 times the limit as x approaches 5 of x. And again, we're using the same rule as that first one now, which is rule number 3. Okay, and then we want to be able to use the law when you have a limit as x approaches 5 of that constant. Well, whatever that constant is, since there isn't a variable, then that's rule number 7, which means that the answer is going to be 4. Okay, and that rule is rule number 7. Okay, now we're not completely finished yet. We're almost there. Okay, so now what can we say about the limit as x approaches 5 of x squared? Well, now we can now put in the limit of 5 into our limit function. So this now becomes 2, okay, times, well, what are we going to substitute in for x? Well, the limit is approaching 5, so it's going to be 5 and then squared. Okay, and that is rule number 9. Okay, and then we have minus 3. Okay, the limit as x approaches 5 of x would then just be the number 5. And again, we're using the rule number 8. And then this becomes plus 4. It remains 4. Okay, so now we can do is just do order of operations. So we have 2 times 5 squared, which is 25, which gives you 50. Minus 15 plus 4. Okay, so that gives you an answer of 39. Okay. Now let's take a look at example part B. Okay, so let's take a look at part B. And again, we're going to note down each step. So the first thing we want to do is that since this is a quotient law, we need to separate the limits for the numerator and denominator. So we have the limit as x approaches 2 of the numerator, which is x cubed plus 2x squared minus 1. And we're dividing that by the limit as x approaches 2 of the denominator, which is 5 minus 3x. Okay, now by using the division rule, that rule was number 5 of the limit law. Okay, so it might be handy to have those limit laws, on paper or written down in front of you as you're going through this until you get used to them. Okay, so now we're going to expand the numerator. So we have the limit as x approaches 2 of x cubed plus the limit as x approaches 2 of 2x squared minus the limit as x approaches 2 of 1. Now let's write down what each one represents. Well, this one is 1. This one is also 1. And then this last one, subtraction, which is 2. Okay. Let's take a look at the denominator now. So we have the limit as x approaches 2 of 5 minus the limit as x approaches 2 of 3x. Okay, now again, what are the properties used there? Well, we used 1 and actually 2, because 2 was subtraction. So we're actually using 2 there. Okay, so now let's continue. So now let's evaluate the first limit up here in the left. Well, as x approaches 2, it's going to be 2 to the third power. And actually, these all should be negative 2. So let me make that correction. Okay, so we have negative 2 to the third power plus 2 times the limit as x approaches negative 2 of x squared minus 1. Now again, we're just writing down what are the specific limit laws. Now for the first one, this limit law is number 9. Okay, the second one is the constant. So that one is limit law number 3. And the last one is 7. Now let's take a look at the denominator. Okay, so the limit as x approaches negative 2 of 5, well, that's going to give you 5. Okay, and the limit law of that is 7. Okay, and then minus 3 times the limit as x approaches negative 2 of x. And that represents 3. Okay, now we can expand a little further. And again, we're going step by step so that we understand what are the limit laws. Eventually, you're going to get used to knowing those limit laws, but it's really important to break it down first and not kind of rush ahead so that you understand each particular limit law as you go along these problems. Now, negative 2 to the third power is negative 8. Okay, and then this becomes plus 2. And applying rule number 9 is now negative 2 to the second power. So that is rule number 9. And then minus 1. And we have 5 minus 3. Now apply the limit as x approaches negative 2. So that's going to be times negative 2. And that represents limit law number 8. And now we can just use order of operations. So we have negative 8 okay, plus 2 times negative 2 squared, which is 4 times 2, which is plus 8, minus 1, all over 5 plus 6. And so therefore what's left is negative 1 over 11. And there we have the solution to part B. Okay, let's go to example number 3. All right, so before we get to example number 3, okay, note that if we let f of x equal 2x squared minus 3x plus 4 and then find f of 5 in 39, in other words, we would have gotten the correct answer in example 2a by substituting 5 for x. Similarly, direct substitution provides the correct answer in part B. So the functions in example 2 are a polynomial and a rational function respectively. And similar use of the limit laws proves that direct substitution always works for such functions. Okay, so we state this fact as follows. Now, direct substitution property, if f is a what? It's a polynomial or a rational function, and that a is in the domain of f. Then we can say that the limit as x approaches a of f of x is equal to f of a, meaning that we can use a direct substitution if it's a polynomial or a rational function. Okay, now functions with direct substitution property are called continuous at a, and they'll be more covered in section 2.4. However, not all limits can be evaluated by direct substitution, okay, as some of the examples that we're going to see soon. Okay, so let's find the direct substitution of the limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, so let's do this in two ways. Okay, so the first way is, if we take a look at this law, we have the quotient. So let's separate this by using the limit as x approaches 1 of x squared minus 1 divided by the limit as x approaches 1 of x minus 1. Okay, now if we separate this using our limit laws, then we have subtraction in the numerator and in denominator. So we would have the limit as x approaches 1 of x squared minus the limit as x approaches 1 of 1 all over the limit as x approaches 1 of x minus the limit as x approaches 1 of 1. So if we plug in direct substitution here, since this is a rational function, plug in 1 in for x, square it, gives you the value of 1, minus the limit of the constant is 1. And in the denominator, the limit as x approaches 1 of x using direct substitution becomes 1, minus the limit of that constant is 1. So what do we get here? Well, we get 0 divided by 0. Okay. Now, we can also look at this in another way. Let's take a look at this step. So before we even separate the limit, okay, what we can do is we can use some of our tools from algebra. So, and what I mean by that is we may be able to simplify this rational function first. Well, can we factor x squared minus 1? Well, according to difference of squares, yes, we can. So we have x plus 1 times x minus 1 and then we're dividing that by x minus 1. Now we can see here that we can simplify that and get the following limit as the limit of x approaches 1 of x plus 1. Now if we use direct substitution here, we can apply 1 in here, right? Or we can expand it. Eventually you can just use direct substitution. So plugging in 1 in for x and then adding 1 is what? 1 plus 1, which equals 2. So what you can see here is that we're getting two different results. Okay, now what I want you to notice here is that for this graph, okay, and I want you to see this graph. Okay, now if you look at this rational function here, okay, now technically what is not in a domain? Well, we know that what is not in a domain would be 1, and that's 1 minus 1, which would make this undefined. So if you notice here that when the value is 1 and the output is 2, you have a hole here because it's undefined at that particular number. But again, we still have this line of x plus 1. This is what our graph would look like after we simplify this. Now, if we go back to what we talked about with limits, okay, it doesn't have to equal the value. We just know that as x is approaching 1 from the left and from the right, that we can see that the limit is 2 and not the first situation. So we need to be careful on how we go about solving these problems. So direct substitution didn't work for the first step. But for the second one, what do we have to do? We had to use some of our algebra tools to factor, then to get us the correct limit. So that gives us another definition here. So in that previous example, we were able to compute the limit by replacing the given function by a similar function by factoring and getting the function x plus 1 with the same limit. Now this is valid because f of x is equal to g of x except when the value x is equal to 1, which again created the hole. And in computing a limit as x approaches 1, we don't consider what happens when x is actually equal to 1. So in general, we have the following useful fact. Now if the function f of x is equal to g of x when x does not equal a, then the limit as x approaches a of f of x would equal the limit as x approaches a g of x, provided that the limits exist. All right, let's take a look at example number 4. Okay, so in this example, we have the limit as x approaches 1 of g of x. Now, g of x is split into two functions. It's when x plus 1 if x does not equal to 1, and pi when if x is equal to 1. So what it's saying here is that the function g is defined at when x is equal to 1. Okay, and what that means here is that it's defined because g of when x is equal to 1 is the output of pi. And again, that's given. Okay, but the value of a limit as x approaches 1 does not depend on the value of the function at 1, meaning what it's equal to, like we talked about in the previous example. Now, since g of x is equal to x plus 1, for x does not equal to 1, then we can say that the limit as x approaches 1 of the function g of x, okay, would equal the limit as x approaches 1 of x plus 1. And so again, using direct substitution, the number is going to be 2. So basically, even though it's given that the input at 1 is equal to pi, it doesn't matter if it's equal to that number because the limit is still following this scenario. So let's take a look at the graph. Okay, so here is our graph. So we first graph x plus 1 if x does not equal to 1. So again, we have our line where the hole is there, okay? And then we also plot the point g of 1 equals pi. So that means 1 and then pi, which is about 3.14. Okay, now this point is irrelevant because it equals that number. We're looking again at the limit of that function. So the values of the functions in both of these examples are identical except that when x is equal to 1. So they have the same limit as x approaches 1. Okay, let's take a look at example 5. Okay, example 5, you want to find a limit by simplifying the function. Okay, so let's go ahead and rewrite this. So we have the limit as h approaches 0. Okay, so before we do anything, before we use our division rules or our quotient rules, let's expand 3 plus h squared because we know that we need to multiply that out, okay, in order for us to be able to simplify this limit. So 3 plus h squared is the same thing as 9 plus 6h plus h squared minus 9 all over h. Okay, so now that we've expanded the numerator by multiplying that out, we can see that we can eliminate the 9. So now we can write this down as the limit as h approaches 0. So the 9's are no longer there, and we end up having, if we rewrite this, we should have h squared plus 6h divided by h. Okay, now again, before we take the limit of this function, can we do something in a numerator? Well, we can because we know that they both have a common factor of h, so we can factor that out. So now we have the limit as x approaches 0, and we can factor out the h, and what's left is h plus 6 divided by h. So now we can simplify the h's. And so now we have the limit as h approaches 0 of h plus 6. Now I also want to keep in mind here that at this point now we can use direct substitution. And when you use direct substitution, you no longer write the limit. So if you keep writing the limit in this next step, it would be incorrect because now you have to use direct substitution. Direct substitution meaning now h is going to be applied to be 0. So we have 0 plus h, which gives you the value of 6. Okay, now in example number 6, we're going to be calculating a limit by rationalizing. So let's go ahead and write down this limit here. So this is the limit as t approaches 0 of the function the square root of t squared plus 9 minus 3 divided by t squared. Okay, now when we rationalize, we want to be able to multiply by its conjugate, meaning what is the conjugate of the numerator. And so the conjugate of the numerator would be the square root of t squared plus 9, and that would be plus 3. And you'd be multiplying the denominator by the same thing. So you'd have the square root of t squared plus 9 plus 3. So now when we multiply this out, well, what happens here is that we multiply that numerator, and we multiply the numerator together, then we're multiplying the difference of squares. So we're going to square the first term. When you square the first term, that means you're going to be removing the radical sign. So you're going to have t squared plus 9. And then you're going to have minus 3 times plus 3, which is going to be minus 9. And that's going to be divided by t squared times the square root of t squared plus 9 plus 3. Okay, now what we notice here is that when we combine like terms in the numerator, that 9 minus 9 becomes 0. And now we end up having the limit as t approaches 0 of t squared all over t squared times the square root of t squared plus 9 plus 3. Okay, so from here now we can actually simplify t squareds and be left with 1 in the numerator. So now we have the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. Okay, now we can use our definition of the quotient rule, or quotient law. And so we now have the limit as t approaches 0 of the numerator, which is 1, over the limit as t approaches 0 of the square root of t squared plus 9 plus 3. Okay, so now if we evaluate the limit in the numerator, well, it's a constant, so the limit as t approaches 0 of 1 is going to be 1. And now let's expand the limit in the denominator, so we're going to have the limit as t approaches 0 of the square root of t squared plus 9 plus the limit as t approaches 0 of the constant 3. So now we end up with 1 in the numerator still. And now using the definition of the square root, okay, we can see that you have now the square root of the limit as t approaches 0 of t squared plus 9 plus the limit of the constant 3, which is going to be 3. Okay, now under the radical we can now use substitution. So we now have the square root of 0 squared plus 9 plus 3, which ultimately gives us the square root of 9 plus 3 in the denominator, which is 1 over 3 plus 3, which gives us the result of 1 over 6. Okay, so now some limits are best calculated by first finding the left and right hand limits. So the following theorem is a remainder of what we discovered in section 2.2. It says that a two-sided limit exists if and only if both of the one-sided limits exist and are equal. So the theorem states that if the limit as x approaches a of f of x is equal to L, if and only if the limit as x approaches a from the left and the limit as x approaches a from the right is equal to L. So when we're computing one-sided limits, we use the fact that the limit laws also hold for one-sided limits. So let's take a look at example number 7. Okay, we want to be able to find a limit by calculating left and right limits. Okay, and we want to be able to show that the limit as x approaches 0 of the absolute value of x is equal to 0. So we need to recall certain definitions that we've seen earlier in our discussions. We can see that the absolute value of x is a piecewise function. And the definition states that absolute value of x is equal to x if x is greater than or equal to 0. And that it's negative x if x is less than 0. Okay, so let's take a look at when we can see that the absolute value of x is equal to x for when x is greater than 0. We don't need to be concerned of the equal because we talked about that in the past. We're not concerned about when it's equal to 0, but we do want to figure out when x is greater than 0. So in order to do that, let's take a look at the graph. So we know what the graph of an absolute value function is, okay? So if we're looking at this first part of absolute value of x is equal to x, that means everything is greater than 0 on this side. So what we're trying to do is, okay, what is the limit as x approaches 0 from the right? So we would say that the limit as x approaches 0 from the right of the absolute value of x would equal the limit as x approaches 0 from the right of x, which we can see that on the graph, or if we plug it in, we can see that the answer is going to be 0. Now, we also need to look at the other piece, which is when the absolute value of x is equal to negative x for when x is less than 0. So now we're looking at the other side of the absolute value function. Okay, so we can say that the limit now as x approaches 0 from the left of the absolute value of function, okay, is going to equal the limit as x approaches 0 from the left of negative x. And we can see that it also approaches 0. Now, because of the fact that the left and the right limits are approaching the same value, then we can ultimately say the following. We can say that the limit as x approaches 0 of the absolute value of x is going to equal. So that limit as x approaches 0 of the absolute value of x ultimately equals 0. Okay, now let's take a look at example number 8, where we want to prove that the limit as x approaches 0 of the absolute value of x divided by x does not exist. So let's start with the left-hand side. So if we want to take a look at the limit as x approaches 0 from the left of the absolute value of x divided by x. And so by definition, we know that the absolute value of x, when you're looking at the limit from the left, and that's from our previous example, is going to be negative x over x. Now, can we simplify this, meaning negative x divided by x? Well, what does that equal? Well, technically, that just equals, when we simplify that, negative 1. Now that is a constant. So the limit as x approaches 0 from the left equals a negative 1 is going to equal negative 1. Now let's take a look at the right side. So we want to figure out, okay, what happens when you have the limit as x approaches 0 from the right of the absolute value of x divided by x. Now again, because you're talking about on the right hand side, we know that the definition of the absolute value of x on the right is where x is greater than 0. So taking a limit as x approaches 0 from the right is positive x over x. Now when we simplify that, we would end up with x divided by x, which gives us 1. Now since that is a constant, then that means the limit there is equal to 1. Now these do not equal each other, and since they do not equal each other, then we would say that we proved that this limit does not exist. Now let's take a look at example number 9, which is the greatest integer function, which is defined by the following. So you can see here the definition of that is equal to the largest integer that is less than or equal to x. Okay, so for instance, okay, the greatest integer of 4 is equal to 4. The greatest integer that is less than or equal to 4.8 is 4. Okay, the largest integer that is less than or equal to pi is 3. And the largest integer that is less than or equal to square root of 2 is 1. And the largest integer that is less than or equal to negative 1/2 is negative 1. And so what we want to do is we want to be able to show that the limit as x approaches 3 of the greatest integer function does not exist. Okay, so let's take a look at the first part. Now, when we talk about the greatest integer function of x, okay, when it's equal to 3. So what that means is that x is greater than or equal to 3, but it is less than 4. Okay, so that's important to make sure that we know that. Now, we want to compare the two limits. So we have the limit, okay, of, let's see here, x approaches 3 from the left, okay, of the greatest integer function of x, okay? So let's take a look at that. So as x is approaching 3 from the left, okay, so from the left as x is approaching 3, okay, well, it's equal to 3 at 3, but the function is approaching 2, so that is equal to 2. Okay, now if we want to find the limit of x where x is approaching 3 from the right, of the greatest integer function here. Okay, now again, looking at the graph, as you're approaching 3 from the right, okay, well, that limit is actually the value of 3. Okay, so we can see here that this does not exist. And so by theorem 1, since those aren't equal to each other, then we can confirm that the limit does not exist. Okay, now the next two theorems give two additional properties, okay, of limits, but both can be proved using the precise definition of a limit which is located in Appendix D. So in number 2, we can see that the theorem, if f of x is less than or equal to g of x, when x is near a, except possibly at a, and the limits of f and g both exist that x approaches a, then we would say that the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. So here is the function g, and here is the function f. So we're saying that this limit for this function f, okay, at a, is either going to be less than or equal to this function g of x as x is approaching a. And so what that does is that allows us to use what we call the squeeze theorem. Okay, now what does the squeeze theorem say? That if you have a function g of x, which is in red, okay, and it's in between the two functions f of x and g of x, when x is near a and except possibly at a, then we can say the following. We can say that the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x is equal to L. Then the middle function that's in between those is also, the limit is also L. So what the squeeze theorem, which is sometimes called the sandwich theorem or the pinching theorem, is illustrated in this figure of what we just talked about. Again, it says that g of x is squeezed between f of x and g of x near a. And so if f and g have the same limit, L at a, then g is also forced to have the same limit L at a. So this limit is used quite a bit in this class. So let's take a look at example number 10. Okay, example number 10, okay, is asking us how to squeeze a function. So show that the function or the limit as x approaches 0 of x squared of the sine of 1 over x is equal to 0. Okay, first and foremost, okay, what do we know about the sine function? Well, we know that the sine function is going to be in between -1 and 1. Okay, so we're going to look at this function here since it is in between y equals x squared and y equals -x squared. So what it's saying here is that this sine function in the red is in between. Okay? Now we also know that according to our trig rules that the sine of 1 over x has to be in between what two values? But again, according to our definition of sine, we know it has to be in between -1 and 1. Okay, now if you take a look at this function here, okay, what is happening to the sine of 1 over x? Well, it's being multiplied by x squared. Okay, so what we want to do now in step number 1 is, since we have 3 items now here in this compound inequality, we're going to want to multiply each side by x squared. So for step 2, we're going to take x squared and multiply it by -1. And again, we're going to take x squared and multiply that by the sine of 1 over x. And less than or equal to, again, we're taking x squared and then multiplying that by 1. Now, once we multiply that all out, we can write step 3. So now we end up with negative x squared, which is less than or equal to x squared times the sine of 1 over x. And so now we can see that this is the function that we were looking for with that limit in our question, and that's going to be less than or equal to x squared. Okay, now what we want to do is, since the limit of what we're trying to find as x approaches 0 of this function, well, we're going to take the limit of all three sides for the same as x approaches 0. So in step number 4, we take the limit as x approaches 0 of negative x squared, which is less than or equal to the limit as x approaches 0 of x squared times the sine of 1 over x, which is less than or equal to the limit as x approaches 0 of positive x squared. Okay, so in step number 5, what we can do is we can determine now what are the limits on the left and the right side of this compound inequality. Well, the limit as x approaches 0 of negative x squared, well, you can see here that it is 0. On the right side, okay, the limit as x approaches 0 for y equals x squared is also 0. Okay, now because of the fact that it's 0 on both sides, then we can say that by the squeeze theorem that the limit as x approaches 0 is in between those two values, so that means it also has to be 0 by using the squeeze theorem. So ultimately now, because of that, we have proved the fact that the limit as x approaches 0 of the function x squared times the sine of 1 over x equals 0 by using the squeeze theorem. Now again, when you're proving that, you need to show it like we just did by using the inequalities so that we are able to prove the fact that you're using the squeeze theorem. Okay, now we can also calculate a limit by rationalizing. Okay,